Hi everyone, I'm Faez Ahmed. I lead the Decode lab in mechanical engineering. And today I'll mostly be talking about things that my students have been doing for the last 3 years. We are about a 3-year-old lab in mechanical, mostly working on artificial intelligence and engineering design.
Have you stay by that podium, just to
Sure.
yeah, make sure the mic is
Oh, yeah, this is better. Great. So what I'll talk about is engineering design and AI. So first I wanted to start with the definition of engineering design, like what is engineering design? And different people have very different meanings of design. So just to be clear, it can mean a lot of different things from sketches, models, robots, manufactured products. In general, design is creating the plan for product systems or services based on some technical or functional requirements. And then manufacturing is making a real product out of those plans. Now, with that definition clear, like if I talk to one of my friends, Mike, who works in the car industry, and I ask, like, what's your design process? He would talk about like defining the user persona, competitor analysis, doing a conceptual sketch, and go on and on. But most people who have worked in design would know that the process is really complex, and you have to go back and forth a lot of times. And as a result, there is difficulty meeting constraints, time and efficiency loss, communication burden, and people don't explore enough. They have one design.
Building occupants. MIT Electrical Services will be conducting a test of the building fire alarm system.
OK.
Unless you are instructed otherwise, please disregard all fire alarm alert tones, voice messages, and flashing lights. At the conclusion of this testing, an announcement will be made to indicate that all fire alarm testing has been completed.
All right, we'll see.
Attention building
OK.
occupants. MIT Electrical Services will be
I just paused
conducting a
then.
test of the building fire alarm system. Unless you are instructed otherwise, please disregard all fire alarm alert tones, voice messages, and flashing lights. At the conclusion of this testing, an announcement will be made to indicate that all fire alarm testing has been completed.
Continue? OK. Great. So the design, I think there is an understanding that there is a lot of life cycle cost of a product is decided in the early stages of design. And today we'll be talking about how can AI enable humans to create better designs faster. Today, there is a lot of things in it. I'll specifically be focusing on deep generative models and how it combines with optimization methods. So first of all, what is generative AI? I'm assuming since you all are in the room, you already know about it. But in a layman's term, I want to explain it's given a sample of data. We want to fit a model to approximate this distribution. It's nothing complex. You have a histogram, you're fitting it. Once you know it, you can sample from it. If you're like much more complex, then you are somewhat like sampling it in a conditional way. Why are we talking about it now? Why is it all over the news? I mean, you can see this image from 2021. This is a group of elephants walking in muddy water, 2022. And this is latest from DALL-E 3 in 2023. And we are seeing a dynamic disruption of text, image, and video domains. The question we think about is, what about engineering? Like, there is a huge improvement in quality, right? But when we think about engineering, there is a lot of issues that generative AI faces. And I'll not go through all the issues. I'll talk a bit about issues around precision, where you are trying to create things that have to satisfy some constraints and performance requirements. I'll also talk a bit about novelty. And there is a ton of examples where you can see things that look very nice, but they won't work. And this is a key challenge that we think about. And specifically, we are very interested in this topic on how can we create the next generation of AI, which has the capability of impacting design and manufacturing. All right, so I'll start with first a set of problems where, as engineers, we need to go beyond statistical similarity. What does that mean? We'll start with a simple problem where current optimization methods do extremely well. So this is like airfoil design is a good, well-solved problem, adjoint solvers. People have been working on it for decades. And what if you take a big collection of designs of airfoils and train a generative model? You can pretty much, in this case, you can see there is an image of all the airfoils that are generated, and it does what it is supposed to do. It mimics the data. But it's not good enough, because it never comes up with designs that we have not thought about. And this is the first problem we started looking at, combining this idea from determinantal point processes and probabilistic modeling on how do we combine those with generative models. along with combining with performance estimators. So in this case, the performance estimator is a CFD modeler. It could be a lot of other things, structural dynamics, people's preference, and so on. So with that, once we can combine these models, again, I'll not go into all the details, the initial result was very promising. We could find designs that were outside the training data. So the envelope is what we were trained on. The green dots are what we were trained on. The model could find things just outside the design, but also the darker pattern shows that they were higher quality. In this case, about 28% higher quality on average. Very promising. But then people would ask, why do we want to use generative AI problem for something that has already been solved, right? And the question is, why not? I mean, why don't we just combine generative AI with optimization approaches? So this is what we did, and there are many ways to do this. The one approach which we started with was something called latent space optimization, where we took the generative model and then took our optimizer and combined them. And essentially, in this case, we found that there were almost 200% improvement compared to some of the state-of-the-art baselines. So SVD, FFD are your standard Bayesian optimization parameterization. Then if you just take off-the-shelf GAN, you get almost similar performance as SVD. And in this particular paper, we got 200% improvement over the existing designs. So we could get something novel, and we could get something which is high performance, which was very promising.
Attention,
Right.
building occupants. All testing of the building fire alarm system has been completed.
Awesome.
Any fire alarm alert tones, voice messages, and flashing lights from this point forward indicate an actual fire alarm event. Please respond to the fire alarm message, and if the alert tone on this floor sounds, evacuate the building.
All right, I hope you don't.
Attention, building
Okay.
occupants. All testing of the building fire alarm system has been completed. Any fire alarm alert tones, voice messages, and flashing lights from this point forward indicate an actual fire alarm event. Please respond to the fire alarm message, and if the alert tone on this floor sounds, evacuate the building.
Great. So we could do this for airfoils. We could also continue on thinking about other types of problems. In this case, we are designing aircrafts, just 3D models where there are constraints. And we want the generative model to adhere to constraints. But one of the key issues when you're applying these generative models for performance and constraints in engineering design is there's a lot of data bias. Most of the data in this particular case was in 12% of the space. So most models that are trained out there actually look very good because the train and test is in the same range. But when you actually test them outside the range, they perform terribly. So this is something we've addressed in one of our work around range GAN, where we said we can actually self-augment the data and take out some of the bias using diversity losses and a few other tricks of training these models. With that, again, we are thinking about going beyond statistical similarity. What does that mean? Statistical similarity means the generative model is trying to mimic the training data, which is great if the training data is like human faces and images. But in engineering, we care about performance and constraints. So we have to think about other metrics. We looked at another problem around topology optimization, which was very well introduced by Josephine today morning, so I'll not talk about what it is. You're given some material, some boundary conditions, and you are asked to generate a design. And we wanted to see like some of the state-of-the-art generative models that on paper, using statistical similarity metrics, they look very good. But when you actually look at their performance, in this case compliance and constraints like floating material, they had almost like 46% constraints were not satisfied. So the pixel image similarity is very good, but they're not performing well. So we started thinking about this problem. We approached it from a different perspective, diffusion models, which are like what drives your DALI 3 and so on. And we said we want to solve this problem where we want to take into account these constraints. And the way we did this was along with using the diffusion, the standard diffusion process where your domain is decided by an image, and then your forces and volume and all loads are incorporated. We also added some regressor models, floating material classifier, different models which tell the diffusion model that what's really happening and what we want to achieve. And in this case, we got almost 8x improvement over performance and 11x improvement in constraint violation. But this was also still not very satisfactory because these models were, first of all, trained on a fixed domain. And second, we are always training on the best designs, the optimal designs. So in this paper, which was published in NeurIPS, where we looked at the trajectory the optimization model took to reach the optimal design. Any design is not like the final design. There is an iteration process. And we trained the generative model from that trajectory and found that the model actually performed significantly better in terms of both compliance, speed, and constraint violation when we actually trained it on the entire trajectory instead of just the optimal designs. And this is like super promising. And in fact, there's a follow-up work submitted today morning at ICML where we said, OK, we want to not only just solve this trajectory problem, but we can actually go train on one domain and show the generalization of other domain using ideas from implicit functions. And one of the good things about this compared to topology optimization is that we actually combine those. So whoever is doing topology optimization can just accelerate their topology optimization using data instead of ignoring experience. And you get a lot more diversity. So for the same problem, you don't get a single solution. You get a set of solutions. And you can look up like the diversity of the solutions. And that's something which we incorporate. Great. So one of the key ideas is deep generative optimization provides a promising way to accelerate engineering optimization. And again, I talked to you about like snapshots of airfoils, CAD, and the topology optimization. We have been looking at many other problems from working with Toyota in the car design and also ship hull design, like looking at multiple dozens of objectives and how do you satisfy all those objectives and make these hulls realistic. But a key challenge that we face over and over is there is a lack of data sets. Like in computer vision, there are data sets of like billions of items, while we are restricted to thousands or if not tens of thousands. And this is a key thing my group has been doing. We have released all our code and data set. We have released about a dozen of data sets on our website. If you are interested in a partnership, we would love to chat. Great. So next thing I want to talk about is design copilot. So first problem we started is optimization does great. Second problem, humans mostly try to design themselves, like designing a bike with a company called BikeCAD. We partnered with them where people go, frame builders go and design their bikes. Now you have to think about not only aesthetics, but you have to think about ergonomics, you have to think about CFD simulation and structural similarity and a lot of other things. So we have been working on different ideas around how do we help as a design copilot. I'll give you a menu. If you're interested, you can read some of those papers. One idea is that a person designs an incomplete part, and the generative AI model completes the part. So you design something, and it says, you know what, now I know that these are the different options you could consider based on the past data it has seen. There is also, you can look at the idea of counterfactuals, where you go online, you upload your own image. We have a demo out there. And it will find the optimal designs for you based on not only structural performances, but things like I want a black cyberpunk style road racing bicycle, which looks like this blue bicycle on the internet that I found. So you can do all of this with some of these tools. If you're someone who's interested in actually playing with the model, there is my student who is thinking about a startup, like who's designed a Copilot CAD model, where you can actually go and talk to the model and looked at like how do I design an entire CAD model based on large language model essentially. And the model is not only giving you a fixed point cloud, it's giving you a CAD, and it goes into the CAD software where you can change things as needed. Oh, yep. You can also go from sketch to prototype. This is being presented in Design 2024, where you give only a sketch, and it enables you to come up with new ideas, and then you can actually fabricate some of those models. Great. So there is some promise where we are seeing that generative AI models can be a co-pilot for people. And then the obvious question is, can current GPT-4V model come up as a design assistant? And I think right now we did a large-scale study on testing it for a bunch of models from concept selection, design description, spatial reasoning, material inspection, CAD generation. And we found that some aspects were really promising in generative, like current GPT-4V and so on. Some aspects are really promising. There are promise, but the models are not there yet. I mean, this is a very good example. My student is here who did this, Annie, and we are asking it to generate a simple CAD with the hole which doesn't go through. And every time we give it feedback, like you got it wrong, but over and over, it almost always gets wrong using different types of scripts. So, and again, we want to point out that when we go and talk to industry, like different industry partners, this is the complexity engineers want. They don't want like plates with holes, right? So we are moving in that direction. There is a lot of promise, but we want to highlight that this is an important area where we want to solve these problems. Finally, a type of problem which humans can't solve at all. So this is designing complex design spaces, where I'll take the example of linkage systems, like inverse linkage design, where you're given a target curve. This is my student trying to come up with a design. And it's called mechanism synthesis, used in robots, arms like cranes, and so on. So we want to come up with a mechanism given a target curve. Most people work on 4 bars and 6 bars. There is a lot of theory behind it, like decades of work on how we can do. But what if we want to go beyond it? This is commercial software that's out there, motiongen.io. You can see that you're given a target curve. It kind of achieves it, but not really. So what we did was we created a data set of 100 million planar mechanisms and about 1 billion coupler curves. And then we started training contrastive models. But before contrastive models, just creating this huge resource, which is publicly available, just doing a simple retrieval on this data set already does better than commercial softwares. So we can just go and find the mechanism which is closest given the curve. But then you can guess who the sponsor of the project is. We wanted a mechanism with a single motor. It can work on extremely complex structures. And this is really important from an ML point of view also, because this is both a discrete and continuous problem. And we are learning what is connected to what and where it is. Just to give you only the letter M, if I take the letter M and give you everything and change one node here, everything in red is infeasible. And the equation is about 600 pages. So we are solving that equation in the inverse model. So these are the problems which humans can't solve today. And with a lot of data and generative models, we can show that these models can really provide promising results. And now we are improving and increasing in complexity to do machine design, going above and adding more components. And we've manufactured it. It's an IBM headquarters right now. Again, it can be applied to many other ideas where you have molecules, network systems, and so on. So moving forward, we talked about creating better designs faster, accelerating scientific discovery. I just wanted to wrap up by saying that, I mean, in some sense, I can't write poems. My wife can vouch for it. But then, like, I asked generative model to write a poem about kinematic design, and like it came up with robotic arms with joints so fine, move with grace in a straight line. Amazing work, right? Similarly, like art, you can draw a doodle, and it can come up with very nice art. What we think about is, when can we come up with a stage where this is an example problem from my time in Australia when I was working in industry, where you say, Alexa, design a stand for my railway wagon. And it comes up, understands the requirements and preferences, simulates performance, and generates designs. And this is what we want to aim for. A quick plug, I wanted to say that I'm also teaching a class on artificial intelligence and machine learning. There is a lot of interest, and it's exciting to see the interest in the community. We had huge improvement enrollment recently. So if you're interested in the projects our students did, please talk to me. Also, if your students are interested, I would love to chat. Thank you.